Okay, I think I'll start. Okay, so yeah, today we're going to go through a review of boosting and cover boosting and applications. If you have any questions throughout, just feel free to interrupt me to ask something. So first of all, suppose we're in a supervised learning setting. That's what we're going to be considering for boosting. And assume we want to do binary classification. So we want to classify all data points to +1 or -1, positive or negative classes. Start with just a very basic, intuitive view of boosting. So the basic idea. There's sort of we can think of it in 5 steps. So first of all, let's suppose that we've devised a computer program that can learn or create some sort of basic rule of thumb for doing binary classification. So we can call this some sort of program that gives you a weak learner. So the first one is devise program that returns a weak learner. Okay. Now, second of all, after we've got a program that returns a weak learner, let's suppose we apply the above program to some sort of, so we've got a data set. Let's suppose we apply the above program to a subset of data or to a weighted set of data. Okay, so after we've applied our weak learner to a subset of data, or sorry, after we've applied our program to a subset of data, this returns a weak learner. So it returns one given rule of thumb for doing binary classification. We can write this as obtains one weak learner. Okay, next we take another subset of data and apply our program to the second subset of data. So every time we apply a program to a subset of data, we get a weak learner that gives a classification rule. And finally, after we do that, we get, again, another weak learner. So we obtain, sorry, this is a bit hard to read, but obtain second weak learner. And basically, all boosting is we cycle through these steps repeatedly. So we continue to select a subset of data, apply our program that spits out a weak learner to the subset of data or to a weighted data set. And this gives us a weak learner, and we continue to do that. And in particular, we're going to do this process t times. So this t here is going to be kind of an important variable when we're talking about analysis a little bit later on. So the two things we need to specify when specifying a particular boosting algorithm is how are we going to choose a subset of data, or how are we going to weight the data during each round for all t iterations, or all t rounds of the boosting algorithm. The answer to that is basically we're going to focus on the hardest examples. So the examples that are most often misclassified by previous weak learners or previous rules of thumb will be the ones that we choose, or the ones that are weighted the most in next iterations. And the second thing that you want to specify when defining a boosting algorithm is how to combine the rules of thumb that you've learned. How do you combine the weak learners at the end of the day to give you one final prediction rule? And basically the way that it's done is you take a weighted majority vote over all the rules of thumb for test points to see whether to classify them as a positive or a negative example. More formally, let's define boosting. I'll define it over here. We can define boosting as a general method of converting weak learners into a highly accurate prediction rule. So I've thrown around this term weak learner a lot. Really what we want is some sort of more technical definition of a weak learning algorithm, which I'll get to a little bit later. But intuitively, what you can think of a weak learning algorithm is a procedure that consistently finds classifiers. So consistently returns classifiers, or rules of thumb, also known as weak learners, that are at least slightly better than random. So whose accuracy is better than 50%. For example, maybe 55% accuracy for your weak learners in a typical setting. And given a sufficient amount of data, boosting can prove and construct a single classifier with a very high accuracy. So something like 99%, even if you only have a sequence of weak learners that only have 55% accuracy. So a little bit of history about some of how boosting was created and how we do analysis with boosting. So let me write it over here because it's a little bit easier to read. Okay, so we've got some history on something called Pac, strong, and weak learners. Okay, so boosting's roots are in Pac, which stands for probably approximately correct learning. This is a learning model or a learning framework which was proposed for analyzing basically machine learning algorithms, proposed by Leslie Valiant in around 1984. Sorry, that's a little bit bad erasing job. The setup or goal in Pac Learning is the following. So let's suppose you have a learner who receives samples from some distribution. And we'll call this distribution D. So a learner receives samples from D. Then essentially, you must select a generalization function, which we'll call a hypothesis, from a certain class of functions. So you select some hypothesis, we'll call it H, from a collection of hypotheses. Okay, so this is basically, you can think of this as a way of viewing supervised machine learning algorithms. So obviously you have data, and then you have your supervised machine learning algorithm, which returns some hypothesis for doing classification. So the goal of Pac Learning is, with high probability, to select a function, to select a hypothesis that has low generalization error. Okay. So it's worth noting that you want with high probability. So this is why it's called probably approximately correct. Probability comes from with high probability, you want to select a hypothesis with low generalization error, where the generalization error is the approximately correct part. So that's where the name comes from. Okay, so let's suppose we have some random samples from some unknown distribution D. And now let's try to define what a strong Pac learning algorithm is, which we call colloquially a strong learner. Okay, so a strong Pac learning algorithm, or a strong Pac learner, I'll just read the definition first and then I'll write up a little bit of notes. For any distribution with high probability given polynomially many samples and in polynomial time, if we can find a classifier with an arbitrarily small generalization error, then it's called a Pac strong learner. So we'll say for all distributions with high probability, I'll just abbreviate it WHP, given polynomially many samples, oops, sorry, I'm writing a little small, in polynomial time, we can find a classifier with an arbitrarily small generalization error. We'll do implies get classifier with an arbitrarily small generalization error. Okay. So this is technically what a strong Pac learner is. So we also have a definition of a weak Pac learner, which is what we refer to as weak learners here in our analysis. Basically, it's kind of similar to this. The definition is for any distribution with high probability given polynomially many samples and in polynomial time, we can find a classifier with generalization error greater than or equal to 1/2 minus gamma for some gamma greater than 0. So I won't rewrite this whole thing up, but I'll just say so basically it's the same thing, but it's a classifier with a generalization error that's smaller than a bound, all right. Okay, so it's generalization error less than or equal to 1/2 minus gamma for some gamma greater than 0. So this just basically means that its error can be slightly under 1/2. Or you can also say slightly better than random guessing. So a random classifier would be one that just returns, just noise on its labels. So that would be exactly 1/2 error. Okay, so two famous computer scientists, Michael Kearns and Leslie Valiant, posed the question in 1988, does weak learnability imply strong learnability? So essentially, if we just have weak learners, is it possible to use them in some way to create a strong learner that satisfies these conditions here? And that question was answered in 1989 by someone named Robert Shapiro, who gave a polynomial time boosting algorithm using the definition of boosting that we have above here to basically answer this question. So this was a pretty famous paper called The Strength of Weak Learnability. And technically, the first boosting algorithm that he came up with was not super practical. It's not like Adaboost or something that we have today. But it was just something that theoretically worked to solve this question. And Adaboost was not come up with until 1995, when Freund and Shapiro came up with a practical algorithm called Adaboost, short for adaptive boosting, in their paper, A Decision Theoretic Generalization of Online Learning and an Application to Boosting. So basically next I just wanted to go through a formal definition of the boosting algorithm and of Adaboost in particular. So I'll probably erase over here and do it on this board. Okay, hopefully you can see through the background text. Okay, so the general boosting algorithm. Let's suppose that we've got a training set that you usually see in supervised learning, so a collection of m xy pairs. So this is x1, y1 through xm, ym. Where let's say that all xi's are in some sort of set called capital X and all yi's are in some set called capital Y. And let's also assume that each of the yi's is either -1 or 1. Okay. So basically for rounds, lowercase t through capital T. So for capital T rounds, you do the following steps. You first construct some sort of distribution, so some discrete distribution over your m data points. So we'll say construct distro capital D sub t. So we index it by which round we're on, because we create a new one each round, over your data points m, or we'll just write it out for 1 through m. And second of all, you find a weak classifier, which maps from capital X over to -1, 1, with a small error, epsilon t, which we'll define now. So you find your weak learner. Okay, so one thing to keep in mind is, so we need our weak learner to give an error that's less than 50%. But this error is actually defined in terms of the distribution D that we've written here. So this is kind of one subtle point to keep in mind. So essentially what we need is, so let's first of all define what epsilon sub t is. So epsilon sub t is equal to the probability under I being distributed according to D sub t, that our weak classifier, H sub t of xi, is not equal to the label yi. So this is the probability of it being incorrect under our distribution that we've just defined in this round. And empirically, given the fact that we don't have access to this probability, but just whether something's correct or incorrect on the training data, we can define this as the sum over I such that it's incorrect, such that ht of xi does not equal yi. So you sum over all the incorrect data points of the weight given this discrete distribution on the ith data point. So that's what we're defining epsilon sub t to be. So again, for each round, what you do is you first construct a distribution. You then find a weak learner with some sort of small error on this distribution. And you just repeat through this t, capital T times. And then at the very end of the day, what you want to do, the final step, is to output a final classifier, which we'll call hfinal. And this hfinal is also a map from x to y. OK. So we can see here that we hope that this final classifier is going to be a strong learner. Each of these guys within each inner loop could be a weak learner. Now we'll define a particular case of boosting called Adaboost. So in adaptive boosting, basically if you look at this kind of general boosting algorithm here, there's only a couple things we can specify. One is how to choose our distribution over the data points that we pick in each round. And the second of all is how to basically get a final classifier from each of the weak learners that we've selected during all t rounds. So that's all that Adaboost actually specifies, just those two things. We'll write it over here. OK, so again, the two things that Adaboost needs to specify is how do we construct these distributions dt over the data points at each round, and how do we construct the final classifier. So first let's talk about how do you construct this discrete distribution over these m data points. Which we call constructing the d sub t's. Well, for the first iteration, you assume that there's a uniform distribution over the data points. So d sub 1 is equal to 1 over m. I say d sub 1 of I because it's actually a discrete distribution for each class I. For all I in 1 through m. OK, so we'll construct it as sort of an induction in an inductive way. Given d sub t and your weak learner h sub t, we're going to define d sub t plus 1, so the next distribution in the next round, in the following way. So let's assume we have d sub t and your weak learner h sub t. Then implies d of t plus 1 of I equals d sub t of I. So the distribution from the previous round divided by a normalization constant, which I'll just discuss in a second, multiplied by one of two cases. So the first case is e to the negative alpha sub t. If your label yi is equal to the prediction h sub t of xi, and e of positive alpha sub t, if you have an incorrect labeling. So if yi is not equal to h sub t of xi. And we can write this a little bit more cleanly. I'll write it over here because it looks a little bit more blank as the following. Okay. So this is the final update rule for the t+1th distribution. Your previous distribution for the ith class, so this is like the d+1th distribution, the t+1th distribution for the ith class. dt of I, the previous one, normalized, times exp function of negative alpha sub t, where I'll define this in 1 second, multiplied by your true label, multiplied by the output of the weak learner on the ith data point. So what is this term here? We'll define alpha sub t as the following. Okay, 1/2 of the log of 1 minus epsilon t over epsilon t. Note that this is positive. And also epsilon t here is defined in when we wrote out the general boosting algorithm. We wrote it up here as if you sum over all of the mislabeled points and you take the weight, the distribution weight over each of those points. Okay, so again, this is the update for the distribution in each successive round. Okay, then finally, how do we define the final classifier, the combined classifier after all t rounds? We'll define it here. Okay, final combined classifier, h sub final of x is equal to the sine of the following. You sum over your t rounds and you multiply your alpha sub t, which you computed at each round, times the weak classifier h sub t. So it's really a weighted sum where your weight is given by alpha over your weak classifier. After you take the sum, you take the sign. If it's positive, you assume it's your final classifier returns +1. If it's negative, your final classifier returns -1. So a few notes about the Adaboost algorithm. So the weak learner's error, epsilon sub t, is measured with respect to the distribution at each iteration. So as I mentioned before. Keep in mind that the weak learner could be an algorithm that can use the weights or the distribution d sub t on the training samples in some way, or it could be a distribution, or it could be a weak learner that doesn't use that at all. Also, if it's not possible to actually incorporate the distribution here that you've calculated before getting to the weak learner, if it's not possible to directly incorporate that into the weak learning algorithm, what you could do is take your data points with a distribution over them, sample from that distribution. So now you've got kind of a new set of data points that you've subsampled in a certain way, and then just run just a classic supervised learning algorithm on these new subsampled data points. So this is a way to basically use weak learning algorithms that don't incorporate some sort of distribution over data, that just are used in sort of a normal way by kind of subsampling a new set of data that's according to this distribution. Okay, so this alpha sub t term here that we've defined, you can think of it intuitively as sort of the importance of your weak learner, your teeth weak learner, or your teeth hypothesis. Alpha is always greater than or equal to 0 if your error for the weak learner epsilon sub t is less than or equal to 1/2. So it should always be greater than 0, assuming that you have weak learners that are better than random guessing. Also, another thing is that alpha t gets larger as your epsilon t gets smaller. So this is kind of what you want. You want to have like a stronger weight for each of your weak learners, for each of your hypothesis, is depending on its error. So if it has lower error, you want to have a stronger weight in your final weighted sum to get your final classifier. Okay. So boosting can actually, we'll talk about this a little bit later in various extensions to boosting, but you can actually extend boosting to give confidence rated predictions. So instead of just giving you a plus, or a binary classification, you can actually get a confidence for each of your predictions. So in this extension, essentially what you can get is a hypothesis h sub t of x that instead of being either 1 or -1, that's just in R, where the sign of h sub t of x determines basically the classification. And the magnitude of h sub t of x determines the confidence of the prediction. Okay. And so this is kind of an extension of the typical vanilla boosting algorithm that we've just written a second ago. So some advantages of Adaboost are that it's fast, it's simple to implement, it's very simple to program, as you can see. One big one is that there's no parameters to tune. So a lot of supervised learning algorithms, you kind of have to do some sort of tuning or parameter choosing to get some sort of good results. In this algorithm, as long as you have weak learners that you know are reasonably tuned and they give you some sort of better than random noise, as long as you run this for enough iterations t, enough rounds, it'll give you good classification performance. So that's kind of a cool thing. There's no parameters really to tune at all. You have a flexible choice of your weak learning algorithms. You can really choose whatever you want, and you can choose multiple different things. And you don't have to know in advance sort of properties of these things or how if different weak learner algorithms work in a certain way together, they all operate independently. It's provably effective, and it works for many different types of data in terms of continuous, categorical, binary, whatever type of data. So in class, we also went through a bit of theory that I wanted to kind of recap. So in particular, the first theory we're going to go through, I'll erase this for now, is theory on how the training error decreases as you go through the different rounds of the boosting algorithm. Okie doke. So first we're going to give a theorem on the training error. Let's suppose that we've written our error for each hypothesis, which we've written here as epsilon sub t. Let's suppose we write it in terms of 1/2 minus a gamma, where gamma is greater than 0. So let epsilon sub t equal 1/2 minus gamma sub t. And keep in mind we're kind of assuming here that epsilon sub t is less than 1/2. So we have a weak learner that's slightly better than random noise in terms of its classification accuracy. Then this implies that your training error of your final combined classifier is bounded by the following. Okay, training error of H final. So the first term here is a product over your t rounds of 2 times the square root of epsilon sub t of 1 minus epsilon sub t. Now we're going to write these epsilon sub t's in terms of this gamma formulation here. So 1 minus 4 gamma sub t squared. And finally, we can bound this with the following. This is less than or equal to x of -2 times the sum over your all capital T rounds t of gamma sub t squared. We're assuming that we could have for each of the capital T weak learners, we could have a different error epsilon sub t and therefore a different gamma sub t term here. But there's a corollary of this, which I'll write up here. Did I erase some of these things? Let's assume that for all t, we've got a term gamma that is less than this gamma sub t here. So if for all t, the gamma sub t is greater than or equal to a term gamma, which is greater than 0. So this basically means, note that gamma sub t is kind of the amount that your error is less than 1/2. So a bigger gamma is better. So we're kind of assuming we've got some gamma term that is worse than all the weak classifiers. This implies that the training error of the final classifier is less than or equal to exp of -2 sum over the t rounds. Oops, that's all right. -2 gamma squared capital T. So this here is really kind of the key theorem that you should keep in mind. The main thing to notice is that the capital T here is in the exponent, So this training error for the final classifier decreases exponentially with the number of rounds, capital T. So that's kind of a cool property of boosting, that as you go through the rounds, assuming that you have some sort of gamma that lower bounds the gamma sub t for all the weak learners, then your final combined training error is going to decrease exponentially each round you go through in boosting. So another thing, Adaboost is called Adaboost for adaptive boosting. One reason why it's adaptive is that you do not need to know the gamma or the gamma sub t or the epsilon sub t error for any of your weak learners, nor do you need to know the number of rounds, capital T, that you're going to do. So you could keep running this sort of sequentially in an anytime way, and you don't need to know beforehand any of these terms. So another advantage of boosting that's kind of weird relative to some of the previous supervised learning algorithms that we've seen in this class, and some things you might have seen in the past, are that it doesn't really overfit in a way that you'd expect it to. So I'll draw up a couple graphs. They're kind of similar to the ones we've seen in slides in just a second after I erase. Okay, so in many supervised machine learning algorithms, you'd expect the test error and the training error to kind of have a graph that looks like this. So in our y-axis, we have the error. In our x-axis, we've got, in this case, we'll say the number of rounds in our boosting algorithm. Typically in supervised machine learning algorithms, the thing that you'd see here on the x-axis is like the model complexity, or the complexity of your supervised learning algorithm. So in this case, because every time that we go through a round in boosting, we sort of add another supervised learning algorithm, add another weak learner to the combination, you can kind of think of number of rounds here as the model complexity. So what you'd expect, and what you see in many supervised learning algorithms is this. First, we'll draw up what the training error is. So this is the error on the training data as you go through the number of rounds and increase the complexity of your classifier. It decreases and eventually goes to 0. What you see in your test error is that after a point, the model gets too complex and it overfits to the data, and you get worse performance eventually on your test error as the model complexity increases. So first of all, this is the training error. Well, your test error might look something like this. It would continue to go down, and then after a point, it would start to increase. And essentially, this would be the point here that you want to choose in terms of model complexity. So you might expect that for boosting, you'd want to go to a certain number of rounds and then stop it at a point. But we actually don't see this behavior empirically when doing boosting. So it's funny, in the first boosting paper, they didn't actually have a great explanation for this. So this was only behavior that was explained in further research later on. So using the same axes where this is error. This is number of rounds of the boosting algorithm. You see in practice that the training error decreases as you'd expect to a very low value, but the test error, actually, I'll draw this a little bit differently. training error decreases, till it hits 0 at one point, and then it just stays at 0. The test error decreases, but then just continues to decrease. And after a point, it asymptotes, but it never increases, even as you increase sort of the model complexity, even as you increase the number of rounds, which is very surprising. The other thing that's kind of surprising is that you can notice here on the graph that the test error actually continues. So this is the point here where the training error equals 0. So after this point, usually in supervised machine learning algorithms, the model doesn't really change. When you're learning, you've already gotten 0 training error, so why would you continue to modify the model? However, we see in boosting that after you get to 0 training error, the test error, when you're testing it on your test data set, continues to decrease, which is kind of odd. So why would it continue to decrease? I'm not going to go into too great theoretical detail about this, but the basic idea has to do with margins. So we can analyze the generalization error by considering the margins, and we can basically see that they widen even after the training error is 0. And when you have wider margins, in some ways you get better classification and sort of a simpler model. So I'll write up the outline or the intuition behind 2 theorems that kind of explain this behavior. Okay, so the first theorem, this is a sketch, but it basically says in a much more technical way than this, that large margins implies better bounds on the generalization error. So we just assume that if we get kind of large margin classifiers, that we get some sort of better bound on our generalization test set error. Okay, the second theorem's sketch of this theorem is that boosting tends to increase the margins of the training examples even after the training error is already 0. We'll just write here, boosting increases margins. And just kind of some intuition that ties into what we see here with usually in supervised learning with model complexity is that although the final classifier, H sub final, is getting more complex as we increase the number of rounds, the margins are also increasing. What this means is that the final classifier is actually getting closer in some ways to a simple classifier. Even though it's from a more complicated class of functions, it is more similar to a simple classifier. And so you've got this sort of fight between the increased complexity from a more complex class of functions and the decreased complexity by being similar to by the increasing of the margins. And overall, what we have is that the test error decreases and eventually asymptotes out and doesn't seem to go back up. So that's kind of cool. What that means is that you don't really have to worry about finding the optimal number of iterations, capital T, to do boosting. You can just kind of make sure that it runs for a sufficient amount of time until you're getting sort of you're asymptoting, or that you would asymptote in your generalization error, and then you would get good performance. So another cool thing about Adaboost is that we can actually look at the type of loss that this algorithm optimizes. So most supervised machine learning algorithms minimize some loss function. For example, we can have least squares loss for regression problems. It turns out that Adaboost also, in addition to kind of writing it up in an algorithmic way, we can write it up or we can view it as optimizing a type of loss called exponential loss. So I'll erase this for now and then write up what the loss function that this algorithm minimizes. Okay. So it's called the exponential loss. For Adaboost, let's let our family of functions f of x be the sum over the t rounds of alpha sub t, the weight, times h sub t, our weak learner. So this is the final combined classifier that we defined earlier. Then the loss, which we'll write as L, which is a loss over our selected function f. But you can also see that as a loss over our choices of alpha and h is equal to fraction 1 over m times the sum over our m data points of x function of negative yi. So negative our label times f of xi. So essentially we have this loss here, and what people have shown, what people have proven, is that at each round of the boosting algorithm, Adaboost greedily chooses some alpha sub t and some h sub t that minimizes this exponential loss. Another cool thing is that the exponential loss is actually an upper bound on a more typical type of loss called the 0-1 classification loss. And if we're just going to draw a little figure that kind of illustrate these two types of losses, draw it like this. This x-axis is y times f of x. And this is our loss here. The 0-1 loss, if you have below 0, you have 1. And if you have 0, you have 0. So essentially, if things are correct, you have 0 loss, and if things are incorrect, you have 1 loss. And our exponential loss looks instead like this. Kind of like that. Where this is exponential. And this is the 0-1 loss. Okay. So really quick, I'm going to go through just some applications in our last couple minutes that we have here, where boosting's been used to good success. Originally, in the first paper, they just kind of showed it on standard benchmark supervised learning data sets, so kind of toy data sets a little bit. Eventually after, and these were all binary classification data sets. Eventually it was extended to multi-class classification, so you actually can generalize the procedure to do classification for many classes. You can also generalize it to multi-label classification. So for example, if there's greater than 1 correct labels per example in your data set. It's also been extended to ranking problems. So if you want to rank a list of examples, which is kind of increasingly popular task in machine learning, so you can do boosting for this problem. And also, as I described before, it's been extended to confidence-rated predictions. So if for each of your weak learners and final combined learner, you don't just want a single binary classification, but you want a certain confidence level for your prediction, you can do that. And it's also been used with pretty good success in text categorization, which has been used or at least implemented in papers for collect call categorization. So categorizing what kind of call after you've transcribed the words from a call down in terms of people calling collect or things like that. Automatic call answering, outlier detection or spam filtering in call answering systems. And it's also been extended to like an active or semi-supervised learning cases where you start with an unlabeled data set, you perform boosting to see which labels have the lowest confidence, and then you select these labels you select these examples to add labels to, and you iterate through this process, finding out which examples are predicted with low confidence and then getting the labels for them. So this is kind of an active learning sort of framework. And that's pretty much boosting. I think we're just about done with time now. If you guys have any questions, let me know.